back propagation examples, I don't necessarily know that everybody really resonated with it, exactly what was happening in that space. I saw a little bit of disparity between what I had originally expected, which was kind of a little bit more confidence in the execution of the map with a slightly smaller structure. And I would like to sort of go back and revisit that. So I would like to try to have maybe, and I'm going to designate some class time for that. I realize that it's best for us to do an interactive approach. But I'm going to do that in conjunction with some of the principle and theory stuff that we've been framing along. So initially, my initial assumption that I was going to be able to try to give you guys a bunch of stuff to look at over the break that was going to just prep you for a midterm, and it's like I kept finding stuff on the list of things that I would like to ask questions on and going, yeah, we kind of need to do that again or in a little more detail. So what I have actually done is I've flowed the next 2 weeks worth of stuff that's going to give us an opportunity to, all right, let's flesh out all of those elements beyond the, here's a slide, this is a thing, kind of topical analysis, if you guys get where I'm going. All right, and this is something that wasn't exactly done for me. So what I think any instructor really does is kind of the same thing that people do with like their parents. It's like, I want to give my kids all the things that I didn't get as a child growing up, you know? So it's like, that's how I feel like. I'm like, I want to give you good things, you know? So just bear with me on that particular front and we'll get there. So let's see if PowerPoint is going to let me do the thing. No, it's not. So give me 1 second. Apparently I have to log in a different way again. I forgot, it's been a while and now it's asking me to do all of my authentication stuff again. Whenever you step away from these stations for more than a day, they lock you out. It's not letting me do this either. Hold on. So we're going to get real practical today. That's going to be the baseline of what we're really kind of thinking about, because I have a set of, let's see if I can do this here. Come on. Well, I don't know if I'll do this for a moment, so I'm just gonna, oh, there it goes. This is the downside of attempting to do anything. That's up. Okay. Well, that was unnecessarily complicated. Okay, so first thing I want to discuss today is something that I've probably already mentioned to you. I probably already mentioned to you guys as a library framework that you're going to have to become relatively familiar with to develop some of the next few projects we're going to do. All right, so for the rest of this semester, we're going to have something that's going to kind of fall in like a kind of once a weekish schedule when it comes to the projects for probably the next 3 or 4 weeks. Okay, effectively, these should all build on top of each other such that you're not really feeling like you're having to do, complete code operation from scratch, ideally. I'm going to assure you today that even if you do have to effectively build a network from scratch, it's nothing like attempting to code a backpropagation algorithm, okay? It's nowhere near that complicated. Matter of fact, it's really kind of simple. You're going to notice a couple of things about it that are really kind of nice, which is Keras, which was originally developed by a guy teaching PyTorch to a class, a group of students, and they all started developing these macro tools. They're like, well, if I need to build a model that has this structure, or if I want to build this thing, it requires me to do these 8 lines of code in TensorFlow in the background, or in Torch in the background, right? Where I have to tell the embedding layer, I have to tell the connectivity, I have to tell the dimensionality of the element coming in, element going out, operation, process, etc. And they said, wait, it's the same thing every time I implement that type of layer, so let's just build a constructor that we can set over top of it that effectively can instance or implement a layer by calling from layer classes. So it is an object-oriented approach that sits over top of the construction framework of TensorFlow or Torch as a backend for the actual network operation. And one of the things that's nice about it is it's handling a lot of stuff that we used to have to really code and crunch by hand, okay? This class, one of the reasons why I'm sort of reinventing all of the assignments in here is because when I took it and when it was offered even last semester, all of the assignments were given in MATLAB. I know that that's not something that necessarily aligns with all of you guys' experience and background, and it doesn't necessarily transfer real cleanly from a computer science perspective. Now, from an engineering perspective, if you're an electrical computer engineer, MATLAB is such a ubiquitous tool in that space that I don't think it would be a bad idea for you to implement it. And I can even provide you guys with some of the code examples from the MATLAB framework. But functionally, Keras and MATLAB, in terms of the degree to which they provide an abstraction for the operations underneath the hood of the flow of the network, are very similar. It's just going to be a syntax naming convention ideal. I would say that in some respects, MATLAB was probably the preferable framework for quite a while for people that had wanted sort of a low effort implementation for utilizing GPUs. Okay, we talked about the idea that GPUs have the capacity for improving a lot of the functions and operations of these networks, largely because of the fact that they have very speedy local memory, right? They have a lot of compute cores that are designed to operate in parallel with one another. And that is something that we look at and go, I love all of those things when it comes to convolutional neural networks. I love all those things when it comes to backpropagation, because I can develop a lot of parallel execution. Effectively, each wait times each input is what? A parallel operation. They're not dependent on one another. So if I can parallelize that component of the matrix transform process both in the forward and the back propagational layer, I can widthen I can run it on a 4,000 lane highway rather than the 8 lane or 16 lane highway that is your CPU. Okay, while your CPU may technically have a little bit more power with regard to individual execution operation and floating point precision operation, GPUs don't need all of that. So they're able to do a lot more just sort of local fuzzy approximation, which actually plays in well whenever we're trying to accelerate the process. We just wanted to learn, and one of the arguments that we've made in the past is, I don't actually have to fix every single bit of the error in one pass. Matter of fact, it's not likely that I'm going to fix all the error in one pass. So as long as I'm close, right, at each iteration, I should be getting approximately closer to the solution on an iterative level. And as the error tends to reduce, as we tend to converge toward those outputs, we're getting toward the bottom of gradients anyway. Thus, we can pick up a little bit more of the precision. But the other side of it is that we often want our networks to operate in deployment on platforms that have these sort of device capacity, right? So all of our mobile devices now have GPUs integrated in them at some level, right? There is a graphics process unit in here. So if we can create a code process that allows us to do some parallelization with regard to the modeling framework initially, we can test how it's going to work in deployment. We ultimately, when you press something on your phone, where's the usability paradigm? The usability paradigm is you push it, you want it to happen now, right? Matter of fact, you would like it to do like predictive processing. You'd like it to tell what it thinks you want to push before you even get there, and just does it, right? Just reads your mind. So, that's coming, I'm sure. It's coming at some point in time. We don't want Google to know enough about us to be able to do that effectively, or Apple. While we desire it, we don't desire the alternative situation, is which they have a digital twin of your brain sort of, trying to tell you what you're going to expect to do. The argument, though, is how do you reduce the pipeline time? How do you make the runtime execution as quick as possible? Well, parallelization is really a nice, quick way to do that. So one of the reasons why I'm harping on this is GPU acceleration is so much faster with Keras. Like, it is a bear to get it implemented and working successfully with GPU frameworks using CUDA-DNN without Keras over top of it. It's not impossible, it just requires a lot of finesse, and you have to have a lot of sort of specific knowledge on CDNN and CUDA, APS libraries. Whereas once you install TensorFlow, usually it's just going to pull down all that stuff and get it working. Does it work on non-NVIDIA platforms or non-NVIDIA compliant platforms? No, not at least according to my understanding. All right. So if you're planning on running this at local execute, which, to be honest, I don't necessarily think is necessary at the level that we're going to be working with a lot of this stuff, because Colab, as I've already demonstrated for you, is capable of dealing with relatively large data sets. Matter of fact, I'm going to show you the data set that is sort of the trailing edge of what MNIST was originally, that we're actually going to utilize in part of our sample framework. Now, I found this set of slides, they're heavily modified from where I found them originally, but I found this set of slides, and they just so happen to include the same data set that I was looking for. So I'm like, I like these slides because they already have the pictures of them that I want. Not to say that I'm lazy. I didn't say it, that's all I meant, right? So whenever we're seeing something like this, you can assume, one, if it's something that you would like to do at the level you're at, someone's done it, okay? You're not in the novelty space yet. I doubt any of you have had enough industry experience to try to really build a network or try to solve a problem with a deployment architecture that is not going to be on Keras or TensorFlow somewhere, right? So this is a very vertically integrated with the backends as well. The backends actually actively work with the development community to support it and to improve new function macros. So pretty much if there's something you want to build, we're going to look at it. I'm going to show you what Keras.io has in it. It has a full set of directory structures that show you what each of the functions do and how they're implemented. But we're going to walk through the main functionalities and the main workflow of development of a learning model. This is going to be a mixture between review and sort of items of interest. I will try to, as your tour guide, point out the elements as we're driving through on our little bus here, okay? What are our goals? Pre-process the data, build a CNN network, train the network, right? And then understand the implementation using the Keras framework. Okay, pre-processing the data here. We're going to start off with this data set. All right, we already saw the one with numbers, right? One with numbers is simple. 99.97% accuracy with that data set is so much of a breeze with CNNs that it's not really even that fun. However, this one's not that easy. Played around with it. Best accuracy that I was able to produce for testing was somewhere in the neighborhood of 90%. Okay? That was a pretty fun little novel network that we played around with and developed that was workable. Industry standard is 96.7%, all right? That's a really, really good network. That is trained using all kinds of tips and tricks and fancy hoops, all right? Somebody actually took some serious time to do that. Will you guys get up to 96.7% accuracy? I highly doubt it, all right? Like I said, 90% on testing performance, validation performance accuracy was where I effectively stopped because I felt like any of the networks that I was implementing were diverging much more quickly, even whenever I set up more complicated loss function metrics. All right, so let's just bear with me here. Fashion in this is a 10 effective digit classification program that goes above and beyond the basic sort of curves and lines framework of MNIST and instead extracts information about fashion products that have been reduced to grayscale representations, all right? This is still a black and white data set, so we're not quite working with color image data. It does increase the complexity of the processing just slightly. It also increases some of the code complexity, but it's not a whole lot different. So we're just gonna work initially with a grayscale visual representation, and we're not gonna do anything with regard to like segmentation or specific feature extraction. We're just going to develop a classification framework utilizing a softmax output at the last layer to be able to do classification for the output space. All right, we're going to be utilizing a softmax approximator with targeted outputs. So we have t-shirts, trousers, pullover, dress coat, sandals, shirt, sneaker bag, and ankle boot as the individual examples here. All the images are 28 by 28. Right? And there are 70,000 images in the data set. This is a slight misnomer because there are 60K images in the one that you can pull down readily available. I think the additional 10K images are part of another set that's utilized as specifically a testing set for this particular framework. All right? But for our purposes, we're going to start off with the 60K samples that we have readily available from the pull package, and that can be easily implemented in Colab to be able to pull that down so you don't have to worry about bringing it in. But we're going to talk basically or briefly about the kind of pre-processing we have to do with respect to the data sets we're bringing in, okay? So each of these data sets has been stored as an array framework, right? So we're looking at roughly the first 25 samples of the data set. And we're going to start off with the process of dataset structural separation for the creation of two arrays, one containing elements of the training set and the other one containing elements of the validation set. Notice both of those two lines look pretty similar there at the top. But what's happening here?
There are labels also.
Yeah, so we're pulling in both images and labels, right? And we're working with them over a specific index in order to be able to ascertain the training framework images versus the validation framework images. So validation framework images will go in with the remaindered samples based upon that vector framework. So we're going to end up with actually two arrays that's going to be train images and train labels, as well as validation images and validation labels. The last line here indicates test images that are brought out, and that shows test images, test labels already cut out of the original framework. Now, why am I doing that? I'm just utilizing the image input considerations, right? I'm actually not pulling in all images from the whole framework. I'm just pulling in a small subset of them. We know what these are for. Training is what you learn on. Validation is what you test on before you test, okay? Because validation allows us to do something that we haven't really done yet. We've talked about briefly, and that is the notion of assessing the performance of the model on unseen data. But as a result, it does effectively bias at least our interpretation or understanding of the model and can be utilized as a sort of corrupting influence on the model if that were used as testing data, right? We don't want to expose the model to even an understanding of how well it is doing on unseen data. We want that to be totally only available to us visually as humans, okay? Validations can still be used as a methodology for implementation of early stopping, and we have an early stopping validation check framework with what we talked about, which was called patience. That is, how many times the validation has to fail until the system will consider implementing an early stop for that process. Well, once you guys kind of see what we can do with it, right, and sort of how that works, you'll get a little bit more of an intuitive feel on how to set that patience factor. You'll also really kind of get it from looking at the training graphs. Because if every now and again, or seemingly intermittently, the system starts to diverge briefly, and then all of a sudden the validation loss drops again in conjunction with the training loss, right? We can notice that we want to be patient for a little while because the system might start memorizing for a little bit and then realize, oh, I don't need to memorize because there is actually a correlation here. If I make this right series of adjustments, I can get myself out of the pit, I can get myself off a ridge, and I can keep driving down towards an improvement in that process. There is actually a terminology for something that I did not know, and I don't know how modern it is, but it's a little niche, but it came around for my knowledge of it, that they attached a term to it. It's from work by Heinlein, and it's called grokking. Have you guys heard of it? Mm-hmm. You guys have heard of the new large language model that Elon Musk had released from Twitter's backend framework? Mm-hmm. It's called Grok. Oh. The reason why, that's how I was like, why is it called Grok? I don't get this. Grokking is the notion that the network can go along for a long time only learning a small amount, and then all of a sudden it effectively finds a whole bunch of downward gradients all at once and has this massive improvement in overall performance. Right, so long-term training potentiation and then massive improvement in performance, that's kind of the patience of the process. So grokking is a process of understanding that something can take a while to mature into sophistication and create something that's structurally useful for us. So this threefolding process and establishing the scale of how many components of the system we're wanting to put in place. You can also use percentage-based scales to do this division framework, right? So you can actually punch in and Kuros will automatically calculate from the framework scaling how much and of what you're keeping intact. Make sure, though, that you keep track of what indexes you're tracking here, right? The reason why the labels are extracted and the indexes are sort of tracked here is because we want to know whether or not we got a good or bad sub-selection of the set whenever we brought it in for training purposes. But having that linkage between the test values and the labels and the training values and the labels and separating them out is usually the trick to the process here, okay? We look through the system, we can see the necessity to translate and transform the data into the appropriate framework that it needs to have for the TensorFlow or Torch framework to understand it. So Keras automatically handles this conversion for us by utilizing the two categorical option, okay? So since we realize this data is categorical, meaning that there are labels that are associated with groupings rather than some type of regression output, we're going to convert our train, validation, and testing labels to categorical so that TensorFlow through Keras will understand what's going on here, all right? So you can, if you do for Torch, right, you're going to use for torch.keras rather than tf.keras, right? Unless you import Torch as tf, which you can do that as well, which I think would probably be against the Geneva Convention or something. I don't know. I'm not sure what it would be. But you can do that if you choose just to use the direct implementation of this. Obviously, import whatever backend you feel like. Call it whatever you want. This one's just using TensorFlow as the de facto backend. Okay. So once we've converted the outputs to categorical, what do those vectors look like? This is that one hot encoding that I was describing previously. So each of these vectors effectively is an indication of what that 10 neurons that are connected to the end of the network should have on their output. So the back propagation is going to involve comparing that output vector to this vector to compose those 10 error vectors that we're going to have to backprop. So one of the things that's interesting here is that if I use the relationship of a one-hot encoding with the 10D, the 10D vector that's composed of or coming out of the neural network framework, I'm not just getting this as a one-to-one perspective. I'm actually dropping this out as a probabilistic relationship. What is the probability of the intersection of this image's subset of feature characteristics with other elements of the shared categorical images of type, right? So I don't just get one that I think it's a shirt. I get a 56% likelihood that I think that it's a shirt in this particular case. In my opinion, that is actually a little bit more informative than a strict one, or zero kind of approximation of a hard sigmoidal approach. But if you want to try hard sigmoid, you can replace that softmax with a simple binary output for bind max for the output here. Okay, I think it's probably not going to be as effective. So structurally, we use the one hot and the categorical indexing process for a confidence of the probability of the sample being a member of the group. Notice we have a first rank and a second rank probability. This actually allows us to create a slightly more complex loss function for the system. We can penalize it in slightly different ways, right? I can actually include, if for some reason my network were to have a little bit more vagueness in its final process, we're to have some like 56 here, and then something like maybe 30% and 20% for three classes total, right? So it has a first, second, and third guess, and they are ranked according to the quantity of the guess. I might penalize the system if the true case is in the third rank, right? More severely than if it was in the second rank. I might also heavily penalize the system if it's not in the first three ranks, right? I might actually really say, look, not only did you miss it, it wasn't even in your first three guesses. This is pretty rough. So we can scale the degree to which the penalty function operation works and the degree to which we're going to put sort of the scaling factor of the penalty. Usually we'd use that term lambda, right, for something along those lines, because we use eta to reflect the learning rate. So we'd have some adjustable learning rate eta times the error plus some lambda of the relationship of the rank process. We can also use stuff like F1 score, sensitivity, total error output, total accuracy. All those metrics can also be implied and put in place to penalize the network for making specific types of errors. Any of those could just be tacked on to the end. They're not challenging to build inside Keras, because Keras will allow you to do some custom loss functions for adjustment. We're not going to do anything with that at the moment because it is very finicky. Okay, it's one of those things that once you've messed with the data set for weeks, right, then you feel like you're able to sort of get in there and mess around in the guts of it. But we're not going to have that long to play with this. We're going to have a little bit of time where you guys are going to set up some experimental processes, and then you're going to do some data analysis. Okay, so whenever we do something like pre-processing scale operations, this says here, to do, add pre-processing, right? Okay, cool, I like that note. That means, hey, at least it's something on your list, okay? So we can do something like normalization for image operations. We do scale float values to simple 8-bit relationships. And a lot of that is already sort of effectively handled in this script, plus it's also handled in the script that I'm going to provide you guys with, okay? Part of the reason why I'm providing you guys with most of the script that you're going to need in order to accomplish this process is twofold. There are some of you that would go out and try to figure out how to do it from scratch with no pre-existing knowledge whatsoever, okay? Those of you probably would learn a lot, right? But there are also some of you who would just go to the Grand Oracle and type in, give me structure code for this thing, right? And ChatGPT would punch out some, we all know who it is, we all know who the Oracle is, or Copilot, one or the other. It's just gonna kind of barf out some code for you, okay? It's probably gonna work. That's straightforward. And the reason why I say it's probably gonna work is because Keras code is so similar that it's very, very easy to work with. It does not have a lot of structural or even sort of command initialization variance. I actually asked it the other day to provide me with the pseudocode.
Oh my God.
I asked it to provide me with pseudocode. Guess what it did? It gave me Python. I'm looking at it, I'm scrolling down, I'm like, this looks like Python syntax. And I scroll up and it says Python at the top of the block. Scroll up to make sure, pseudocode. Yep. Apparently, Copilot thinks Python is pseudocode. I think that's very reductionist. I think it's like, what is it? Codist. It's codist. It's codist. It's got some biases built into it. Where it thinks Python's just pseudocode. Okay, so we're going to utilize some other methodologies here. We're going to talk about a couple of things that we haven't talked about yet. I'm going to leave it up to you if you decide that you want to attempt to implement these things. Okay. I'm not going to require that you do, because to a certain extent, they may not necessarily improve performance greatly on this particular data set. However, I have seen that some level of augmentation will improve performance here. So part of the best performing models in that upper framework for Fashion and NIST did implement and utilize some of these methods. Now, the first of them is rotational augmentation. If I have one picture, right, and I want to imagine all the different ways that I can see this watermelon, right, how can I do it? I'm going to have to just take and rotate the array, right? That's what I've got available to me. I can't really do much else. Now, if I do this, I've actually created several different versions of effectively the same array, right? The same visual information is there, but what is different about it is its order spatially, which we said if spatial order matters, and if convolutional neural networks are designed to be able to extract the frequency of certain feature elements from the visual data, then it shouldn't matter that I am facing up or facing right side or facing left side for this watermelon slice with respect to the capacity of the system to be able to detect it as a watermelon. Scale invariance, this is a repetition of one of the things we talked about earlier on. Scale invariance and positional invariance, view invariance, is one of the principal goals of convolutional neural network visual processing, because this technique right here would really, really mess with some standard traditional neural network frameworks. Okay? If you do this and you attempt to implement a augmented version on a feed-forward neural network, which we're going to implement on both. We're going to implement the fully connected network version for the FashionMNIST, and then we're going to implement the CNN version for FashionMNIST so that you guys can sort of juxtapose those two together. The code for the fully connected CNN is in Torch, not in Keras, okay, so you get a chance to see what that looks like. And then the convolutional neural network structure is in Keras, right, keeping track of that. Since it contains a fully connected network layer, you'll be able to see the fully connected components at the end of that output layer. So rotation is one of the mechanisms which we use to augment, but we can also use a couple others. Mirroring, right, we flip it around the other opposite direction. Randomly cropping it, all right, this recenters the image such that we have a slightly different array where the same components are present, but now they are present in a different space. And also notice this, scale variation relative to the same subfeatures. If I reproject this image relative to this image, if I reproject them at the same scale of the input array, right? Which, I'm going to say this, for the type of network we have right now, you must do that. Every input must have the same dimensionality. If it is 28 by 28, then it's going to be a 28 by 28. Every single sample has to be that same size. The reason why is because it's stuck there, okay? There are other methods we'll talk about a little bit later on that allow us to be able to have some scale variability. They break things up. They effectively find an ideal subregion, or they rescale the inputs. There's part of a trick here that we didn't talk about. I'm not going to show you the exact processes here, but shearing and local warping processes can also cause a certain degree of augmentation to the data. Personally, I don't think local warping does much. And for you guys, the paper you're reading, everybody saw the paper that I put out, right? Okay. That's the one and only thing that I did do was come up with some questions for you guys on that paper. It was hard for me to figure out what to ask you, okay? Because I read it and I'm like, this is awesome. And then everything that I thought was awesome about it, I'm like, I don't think they're going to understand why that's awesome. But that's part of the reason why I'm like, okay, I don't want to protect you. I don't want to baby you. You guys can go out and find your own stuff. So there is an aspect to it where I'm showing you or I'm explaining to you things that you may not have need of yet. But later on, there's an interesting relationship here that warping operations can somewhat simulate wrapping of objects or reprojections of those objects in space, right? So if I have a two-dimensional plane here and I warp it properly, I can effectively simulate the process of change in angle for the visual approximation. So it's a slight adjustment in the visual field, right? Sort of like a tilt shift filter operation. If I do shearing, rescaling, rotation, and random cropping on a data set, I can take the 60,000 samples that I have of my FashionMNIST and literally create millions. Depending on how I use them, I can radically enhance the variation, the variety of information there. Now, the degree to which that will enhance the training capacity of the network is out, right? The jury's out on that, because more data does not always necessarily mean, more samples does not mean more data.
Okay.
The same data is there. You can do whatever you want to it. You can warp it, flip it, stick it, throw it at the wall, cut it up into tiny pieces, shred it. Whatever you want to do to it, it's still the same thing at the end of the day, right? There's no more info there. Yes?
Yeah, I was thinking with the watermelon, like it has a particular seed pattern, that if you do that enough, it might start picking up on that.
Seed pattern, yeah.
That is an interesting relationship because you have a high frequency component that has, when it's rescaled, it's likely to be preserved because it is so different at the level of intensity, right? So when you have radical shifts at the level of intensity, what you're likely to do is have a seed finding filter. right? It's true. You're going to find some like little black seeds, little black dots on something, right? If there's enough of them in the data set, your data set is going to imply you need a seed finding filter. That's actually how any one of the filters is going to converge toward being a seed finding filter. That's an interesting relationship, though, as a discussion group. Yes, sir.
So, I'm also working on a project. So, the project I was trying to do this. You're telling me if I do the rotation, shredding, and warping, it won't have some effect?
No, I didn't say it wouldn't have some effect. I just said that there was a diminishing return on it. You're going, for a while it will work,
Okay.
right? For a while it will enhance it.
Okay.
What is it enhancing, right? Let me show you something. The next thing I'm going to show you guys here will be of interest to you with respect to you understanding the fact that technically there is no difference between these images. It's the same image. It consists of the same structured items, but what's happened to them? Values have been adjusted and recentered based upon multiple channels of information. So there are, the original image framework was 3 channels of color data. Each of the color data channels have been manipulated in order to try to create different color intensities within that space. Does this bird exist? No. This is a synthetic bird. It's an artificial bird. If I'm only concerned with bird detection, guess what? This might be a really good operation. However, if I'm considered with what? Bird identification, is that going to enhance it, Cheyenne? If I want to identify what kind of bird it is and I made one yellow, and there isn't a yellow one in nature, have I done good or bad?
Bad.
I've done bad because I've given the system a bad example of something that doesn't exist. So for classification and identification purposes, I'm going to have slightly different objectives in terms of what kind of augmentation I'm going to attempt to apply. That's the reason why I say there's part art and part science here, right? This is the thing I was talking to you guys about very early in this semester, is you have to be able to think a little bit higher dimensional with respect to what your goal within the system is in order to make a useful set of adjustments to the data. Now, the cropping, median blur operation, right? Median blur is an interesting operation. Why do we want to apply a blur filter?
So that,
Is every image in the real world in focus?
no.
No, since every image in the real world isn't in focus, if I artificially blur it, that means that the system now has to learn to be able to identify the parrot in a blurred image. There's a relationship between blur operations, right, median and Gaussian blur operations, and the implementation of noise-based augmentation. Now, noise augmentation is similar to the process of dropout if you apply strict threshold to salt and pepper noise, right? Salt and pepper noise is that notion of sort of randomly distributed little salt crystals and pepper crystals, little black ones and little white ones just being sort of shaken on top of the image. Now, why would I want to do that? Ever seen something that's been photocopied a few times? Photocopy of a photocopy of a photocopy?
Oh,
Everyone knows
God.
this, and I'll tell you, I think the most frequent place I've ever seen it in my life is grade schools. For some reason, grade schools cannot keep track of the original copy of anything, right? Every year, the teacher keeps one of the old copies that she made last year for the thing, and then copies it again until it's lighter and gray. It's gray. It's this image down the bottom.
Yes,
okay?
yes,
not,
I agree.
You look at it and you're like, I don't know what that word is. I don't know if there are words on the page. Okay. But the thing is, what do you have to do? You still have to fill out the worksheet, right?
Yes,
so you got to squint and then figure out what it says. How's your brain able to avoid that filtering process? The filtering process is extracting useful from not useful, right? So if getting the information that's of import out of the information that's present is one of the primary tasks of the network, artificially inducing some amount of noise will effectively create a new type of sample. So let's imagine this. Let's imagine that you flip it over, you skew it, you you adjust it with a small median filter blur and then add some noise to it. Do those two images look at all similar to one another? No. Do they in fact have any different amount of representational power? No, because they are the same information. However, what's one of the things we want to stop the network from doing? Exactly. So if I make it to where there are so many samples that you cannot possibly memorize them, that is the reason why big data became the solution to network design, right? I just said, look, I'm going to give you 1 billion samples. There's a lot of them that are the same. I'm not going to tell you which ones they are. Most of them I have just manipulated in some way to make them to where they're actually slightly crappier. Okay? And the reason why is I make them slightly crappier than they're likely to be in the real world. Here's the other advantage. If that's so bad that I can barely visualize it here, and yet I can figure out how to make the network identify the components in this one down here with a relatively high noising factor, guess what it's going to do on a regular piece of data that comes into the system that doesn't have that high noise with an STD of 0.04? It's going to say, ooh, this one's easy, right? Because I trained on these ones where I had both hands tied my back and, you know, blinded in one eye and hopping on one foot, right? So we effectively cripple the network. We make it work a lot harder to extract the useful information out of the system, such that I know I'm being very abusive of the network. I'm sorry, I didn't realize it, you know, in the beginning. But all right, so let's talk about what we're going to do next. All right, so these tools are really useful to us. We'll talk about how these are implemented. You can easily see them in the SRT, but remember convolutions, okay? Why do we want these? They do the spatial thing, right? Yep. They do the spatial feature extraction thing. We really like that. So feature kernel, feature map operations are produced by the convolutional operation of the system. How do we implement these things? Well, we're going to need a couple of different elements to play with. We're going to need to know the depth, which is the number of filters we have. We're going to need to know the stride, how far we're moving the filter at any given step of the comm. And then we're going to need to know the padding we're going to implement, or if we're going to add any padding to the system. Most of the time, zero padding is considered acceptable because a lot of times the data has already been padded with respect to the visual space, right? So most of the images that are in the fashion MNIST are going to have pretty decent borders around the outside of them with something like 5 to 10 pixels of no relevant image information present within them. However, if you randomly crop them, that rule will disappear. So you will have to implement some level of padding if you're planning on implementing something like random cropping, okay? I think you guys can understand and track why that makes sense, because if you drop edges off of the convolutions for some of the randomly dropped edges elements, that's actually going to interfere with the capacity for the filter kernel to be activated appropriately. So keep in mind a couple of different things: the scale by which you crop and the locus in which you're cropping in, and the padding characteristic as well as the stride will influence the scale of the output. All right, so we did it once, but I'm going to have you guys do an exercise where you're going to calculate what the output is in each of the dimensions of your network, right? It's very easy to see it, and actually the system will calculate it for you if you just drop your network in. One of the other things that's funny is if you take your network architecture and you copy it and paste it into Google and say, what are the dimensions of the network, it will literally calculate it and plot it for you. Okay? It will do it.
Oh my God.
So, CNN filter layers. Do what? Feed to the next filter layer, feed to the next filter layer, feed to certain outputs. So what do we need to implement? Okay? We need activation functions at the end of the process. That is a requirement for operation of the activation outputs. So we're going to need to select at least something that fits within this paradigm. Most of the stuff that we have is going to fit underneath of ReLU or leaky ReLU. Why? It's efficient, plus it also is a little bit more resistant to something we talked about called the vanishing gradient problem. So vanishing gradient can happen whenever the network gets deeper. And since this is a little bit more tolerant to the vanishing gradient, it can bring gradients back out of suspended animation effectively, right? They don't go so far into negative territory that they're worthy to be considered in future operation states. So they just stick at 0. Leaky ReLU operation actually has this notion that allows for negative impulses to happen. It's effectively 2 linearities in case. Some more advanced structures will allow for excitation and inhibition by utilizing that leaky ReLU framework. We're not going to talk about max outer ELU at the moment, but sigmoid, tanh, ReLU, and leaky ReLU are all easily implemented, and you can probably understand how they work pretty well with regard to the discussions we've had thus far and just visualizing their performance. Okay, so let's put it all together. Model.add, TensorFlow, Keras, layers. What have I done? I called the core lib, right? I called the class in the lib. I called the subclass, the constructor for that relationship, and then I said which of those members of the subclass I was interested in. So this relationship, this forward sequence call process, just forward dot, if you're doing it in a space where the library is already loaded, guess what it does? You hit dot and it pops up a menu that shows you all the things that you can select from at that level. This is the beauty of learning how to work with this stuff in the modern era, right? When I was first working with code, we didn't have that sort of autocomplete operation to keep us, to show us what was happening. I love it, I use it, I'm not going to lie, okay? Conv2D, filters, this is going to be your depth operation, so filters equal value, kernel size equal size, all right? What happens to kernel size? Notice there's not 2 dimensions here, it's just 1 dimension. So by only calling 1 dimension, what is this kernel size? It's n by n. It's a 3 by 3 kernel, okay? Next element in play here, padding, right? Same as literally says padding equals 0, right? Or you can even leave padding out. You don't have to instantiate it. Padding is actually set to default same.
Okay.
Activation operation. Notice I just have to call ReLU. Now if I want to know how to call the other ones, right? Type in the first of the single parentheses, and it'll allow you to show the auto-completion for each of the activation functions. But I am going to show you just quickly later on the options we have available there. Now, the model in this case is going to work like this, right? We're going to have model, which we're going to call something like sequential, okay? We're not going to do recurrent. This is just a forward sequential network. Input shape, and I have declared the shape of the input space as 28 by 28 by 1 channel being coming in, all right? So this turns the entirety of the input values in the system into a large tensor, a chunk of data, okay? So it'll get trained in little cubes if we're going to be doing it by batch processing. I add my first conv layer, right? I know what that one looks like relative to, look here, input shape has to be declared. Why does the input shape have to be declared? Keras has to know how to tell TensorFlow or Torch what the dimensionality of the layer it's instantiating is or looks like. So it's going to say call layer for the first input scaling, which is the I layer for the convolution as a 28 by 28 by 1 element. Okay, so it's going to instantiate that array inside memory. We don't have to worry about that. We can just tell it what the shape of the data is, and it handles all of the construction on the back end for building the frame of what that whole flow looks like, okay? Once we get done with this, we're going to do a layers, max pool op 2D, and we say pool size 2. So this does 32 by 3 by 3 ReLU on 28 by 28 by 1 with a pool size of 2. What do we think the output of this is going to be? What happens whenever I run a 3 by 3 on a 28 by 28 matrix? How much?
Well, you gotta account for the padding.
We don't have any padding on this one. We're just going to go ahead and clip it without padding. So if I center stride, what happens center stride? The kernel always gets set in the center. The center of the kernel is always set at the edge of the image. So how much is hanging over? One hanging over on the outside, one in the center, and then one to the inside, right? So the first time the convolution runs, it will be slightly empty, right? The whole top L of it will not have anything in it. So it actually has to step over one and down one in order to get all 3 by 3 in order to activate. So the clipping to center is going to take one off of the left side, one off of the right side, as well as one off the top and one off the bottom. So a 28 by 28 matrix will become a 26 by 26 matrix. Okay? Once 26 by 26 has a 2-pool line, what's the output? Pool. This one's super easy. Divide by 2. It's 13 by 13. Because every 2 by 2 pixel region will only have one output, right? So every 2 high and every 2 wide will only be one value in the new matrix. So 3 by 3 will drop to 26 by 26, and then the 2 by 2 will drop it to 13 by 13. Notice we've already done a fairly significant amount of both feature extraction as well as dimensionality reduction. Here's the interesting component. If the original space for conv2D is 32, that means I've got 32 kernels. When I do the operation space here, right, I get 32 and then 64 elements on the output siding, right? So the pooling does 32. I take 64 elements of the input parts, okay? However, if I set stride to 1, I only end up losing 2 total from the whole system, right? So at C28, the input is 14 at 28 by 28 for retention. So if I actually set this right and pad it, I actually end up with 28 by 28 on the output of the comm filter, but then I end up with 14 by 14 on the reduction. So what does the padding earned me? 1 extra pixel.
Woo!
Woohoo! Big deal. Okay, it doesn't really make that much difference. Normally, it's not a big problem overall, and the reason why I say I don't usually focus on padding a lot. So this one's, you can see that easily here in comparison to the calculation. Just those strict mental calculations we're making. So knowing what's passed into the next layer and knowing what the activations are at stake. This last one is a 2D convolution layer that has 64 kernels in it. So 64 kernels on a 14 by 14, which is the padded version of the 2 by 2, come out to 8,256 total features, or excuse me, total parameters which the system can effectively learn, right, at this layer. So 320 in the original spatial layer, and then parms for the extended system is 8,578. Right, so you have 8,000 parameters for only 2 convolutional kernels. This is a big chunk of feature or tunable parameter characteristics present within this system. So it's a lot to tune with only a small amount of data, okay? We already talked about pooling, talked about add pool layers, whatever. Okay, fully connected. Let's just talk about this real quick. Fully connected operations go at the end of the system. We know how this works. And then we're going to implement at the end of the fully connected operation a one-hot sequence binary spatial classification with the softmax op, okay? I can implement layers by adding TF, Keras layers, and instead of doing the COM2D or max pool or whatever else those might be, I'm going to be running dense operation. This is a dense connected network, fully connected. I can see first there is ReLU, and then the second activation, softmax. Notice I see the input spacing here at 256. What happens when I hook up the fully connected layer to the back parms layer? Originally, without the fully connected layer, we had 8,576, right? With the fully connected system attached to the end of it, 814,000 tunable parameters. That fully connected network layer is a chunk of the programmable components of the system. Part of the reason why I want to highlight that is because adding a lot of connectivity for the features that are dropped out of the vectorized kernel, adding 256 individual nodes in that first layer, is a pretty wide layer, okay? So we have 64 kernels acting on the 14 by 14 being fed into 256 neurons acting on the vectorized version of that 14 by 14 by 64 value. So there's 8,000 elements connecting to 256 elements. That's a chunk of information coming in, okay? When I look at something like this, I go, that's probably more than we need, but you'd be surprised at how much it actually does need in order to be able to work, especially if we start by implementing some of those other processes we were describing. Okay, let's see here, how much time do I have left? About 5 minutes. Structurally, there's a lot of different ways to look at this. We can implement something like recurrence. We can look at something like UNet, right? UNet structure is pretty fun. This actually is a link to showing how UNet is put together and how it's implemented as a link structure, right? UNet actually allows us to be able to input values and do scale processing at multiple different levels. Oops, not the one I wanted. All right, I'm going to skip past this here. Batch size and epochs training. We had to pick these previously, but these are adjustable parameters. How many you put in the batch and how many epochs you're allowing to train is something you would normally have to guess for, right? We can allow the system to train for more epochs, but that data augmentation is the solution to the overfitting problem, hopefully. The other thing we can do, or at least some of the data augmentation we talked about, is going to be related in, I'm just going to go forward here. Oh, you can save and load the model as well, right? So once the model is trained, you can export model weights to an HDF5 file, and then you can actually load the trained model again and start over with it. We're going to use the load weights operation to take pre-trained models in the next version of this process. We're going to take pre-trained models and then we're going to apply them to new tasks. All right, so that's what our program 3 is going to be. So we're going to start building onto that framework. So if you save your weights, then you can start over again, right, and train another network without risking that the work that you did on the previous one is gone. There's an interesting thing that can happen here if you do this right. That is, as you're going through and training the models, you can set a small amount of epochs. Look at the performance overall of how the network is going so far and say, see how it's starting out, right? And then it's sort of like, like waiting for a souffle to rise, right? So you're sort of looking in the oven window and you're looking, is it going to come up, right? If not, then, maybe this is not going to work. And somehow we were able to like put it in a stasis field and put it in the freezer, all right? So we put it in like a stasis field and then we go, maybe later, right, if that one was looking good to start with but hadn't quite come into its full flower, we can come back and get it again. So if we train multiple different networks with different parameters, and we look at how they're training for the first 20 or 30 epochs, let's say, and we save each of those relevant networks, and then once we've decided which one we like the best, we pluck it back out, we put it back in, and we let it train for a few hundred more epochs, right? You don't want to let all of them train for a few hundred epochs just because it's not going to always produce anything of merit, right? So let's just consider that we're going to sample and process this idea of trying to see what might happen and experimenting with the framework. I'll just let this in here. Parameterization feature learning operation is going to allow us to look at optimizers, okay? So something like the Keras IO framework here. This allows us to look at other optimizer frameworks, okay? As well as dropout, right? So this is a visualization of dropout. It's like an image with like dirty filter over top of it. If I'm randomly not allowing you to see the whole image through, then I'm forcing you to sort of only make a decision based upon what you can see. It's kind of like a chain link, looking at the world through kind of a chain link fence.
Right.
So you're making decisions based upon a slightly varied and dimensionality reduced masked version of the system. Each of these indicates how the dropout layer and normalization layer are implemented, and we're going to design a tuning process via hyperparametric tuning process, okay? We'll talk about, and we're going to implement here, something called the grid search operation, all right? Keras already has a grid search operation in place. where it will iteratively add on to each of those perimeters and attempt to see which network is providing the best performance. Or you can use the more general Kuros trainer framework above it. Okay? The last thing I want to talk about, and I'm going to talk about this, I'll have to reserve this to talk about in a little bit more detail, and we'll try to implement this later on, is optimizers can actually be implemented for hyperparameter optimization utilizing genetic algorithms. So we can randomly select a population of hyperparameters, and we can sort of breed those networks together in order to try to come up with an ideal set of network configuration elements at the end of the state process, okay? This is probably the most advanced form of hyperparameter optimization trainer that you're gonna come across, but I have some code for us to be able to try to implement this one as well in order to be able to test it, but that will probably happen in an upcoming system. We'll walk through the code for your assignments. I might actually just do that as like a video separately so that you guys can have it and reference back on it. But the main goal of today was just to get you guys familiarized with the fact that Kuros is not as intimidating as it might seem, because once you see one script and you see how the lines are implemented, it's relatively easy to just kind of copy paste and put another layer underneath of it, and now you have a new architecture, okay? There's even a really cool website that you can go to that will allow you to visualize what your network topology looks like and even kind of zoom in on it once you have that in place. So, all right, talk to you guys later on. Have a good week.